with this bad boy. Newton's second law can be summed up as F net equals mass times acceleration. Okay. Another way of rearranging this equation would be A equals F net over mass. Okay, all I did was I just made A by itself and I moved things around. Why am I saying that? Because I want you guys to kind of see a relationship here. If I increase the net force on an object, but the mass stays the same, so if the force gets bigger and the mass stays the same, what happens to the acceleration? If this term gets bigger and mass stays the same, A must get bigger to keep this equal, right? So if the net force gets bigger, the acceleration gets bigger. And that kind of makes sense. You push something harder, it's going to accelerate quicker, right? But if the mass gets bigger and the net force stays constant, what happens to the acceleration? It goes smaller, which again makes sense. If I try to push, a 300-pound lineman versus a 100-pound sprinter, the 300-pound lineman isn't going to accelerate as much as the 100-pound sprinter. So this bottom quantity here is called an inverse relationship. As mass gets bigger, acceleration gets smaller. This top one's called a direct relationship. As force gets bigger, acceleration gets bigger. Okay, and that's true of Newton's second law. Down here on the bottom, I have 4 steps for for solving Newton's second law problems. Draw a free body diagram. After you draw the free body diagram, sum the forces in the x and or y direction. Typically, it's just going to be one or the other. Either there's going to be a net force in the x, or there's going to be a net force in the y. And don't forget to include your signs. Then, once you figure out the net force, you set the net force equal to mass times acceleration, which is what Newton's second law is, and then you solve. Okay, so I'll do some example problems with you guys to give you a feel for what this is all about. Let me zoom in here. All right, so there's a force of 25 newtons east and a force of 25 newtons west is acting concurrently on a 5-kilogram cart. Find the acceleration of the cart. All right, so first thing I'm going to do is I'm going to draw a free body diagram of this scenario. There's my cart as a box. First thing I do is identify the object's weight. That's the force of gravity. And it says that I'm assuming this box is on some sort of ground or whatever, so there's going to be a normal force to it, F sub n. And frankly, we don't really care about these two quantities too much right now because we're more concerned with the things happening in the x direction. And it says that there's a 25 Newton force headed east, or pulling east, and a 25 Newton force pulling west. And I'll even call this negative 25 because it's pointing to the left. What is the net force in the x direction? If you have negative 25 going left, or just 25 pulling left, and 25.8 pulling right, it would be what, Kino? 0, perfect. So you have a net force of 0. So I have 0n equals the mass of this box, which is 5 kilograms, times a. So 0 divided by 5 would give me an acceleration of what? 0, right? Remember, no net force, no acceleration. This is just mathematically showing you that. Okay, no net force, no acceleration. And since there's no net force in this box, it would just stay still. Okay, or keep doing whatever it's doing. Let's do a problem where there would be a potential net force. It says a 0.15 kilogram baseball moving at a speed of 20 meters per second is stopped by a catcher in 0.01 seconds. What is the average force for stopping this ball? Okay, this is a little tricky. Why is it tricky? Because it's going to involve some of the equations from the last chapter. I know. Does anyone remember how to solve for acceleration? Very good. So, assuming this baseball doesn't just like blow through this catcher and put a hole in his chest, we can assume the ball stops in his mitt, right? And so the final velocity would be 0. And the initial velocity, tell us, is 20 meters per second. And it takes the catcher 0.01 seconds to stop this ball. Okay. So by doing this little math problem here, I can calculate the acceleration is about negative 2,000 meters per second squared. And just kind of take my word for it that if you put 20 divided by 0.01, you get negative 2,000 meters per second squared. So that's the acceleration. That's nice. But that's not what the problem was looking for. They want to know what is the force experienced by stopping the ball. So I'm going to bust out Newton's second law. F net equals mass times acceleration. I know the mass of the ball. They tell us that in the problem is 0.15 kilograms. We just calculated the acceleration, which is negative 2,000 meters per second squared. And so if you just take 0.15 times 2,000, you get an F net of negative 300 newtons. And the negative is just telling you a directional piece. It's not really like some sort of mysterious force or something like that. It's just a direction, which really turns out to be kind of irrelevant in this problem. All right, but that would be how you'd calculate it. Cool with that? All right, onward and upwards. Yeah, I can make this work. So here we have a picture of a block on a frictionless surface, and it's experiencing two forces, a force to the left of 12 newtons and a force to the right of 2 newtons. And whoever made this sheet was real nice because they gave us basically a free body diagram here. We don't even need to make one. Right? It says, if the magnitude of the block's acceleration is 2 meters per second squared, what is the mass of the block? All right. So I'm wondering what the mass of this block is. That's my question. And I know the acceleration is 2 meters per second squared. What is the net force acting upon this block in the horizontal direction? Okay, so F net is 10. And would that be in the negative or positive direction based upon our typical sign convention? Okay, negative 10 newtons. So basically, hopefully you're thinking 12 left, 2 right. They would become negative 10. Since the net force is to the left, going 10 newtons, will this acceleration be positive or negative? Okay, good. So it'd be negative because it'd be accelerating to the left at 2 meters per second squared. So to get the mass, I'm just going to use Newton's second law, F net equals ma. The net force is negative 10. The mass, I don't know. And the acceleration is negative 2. Okay. So if I take 10 divided by 2, I should get a mass of 5 kilograms. That'd be the mass of that block. All right. So far we've seen 2 different ways of using like Newton's second law. We've seen it by using just good old-fashioned mass times acceleration to get the net force. This time we're using it to find out the mass. Now we're going to use it, I think, to find out the acceleration, if my memory serves me right. Nope, I lied. Do you have questions on that? Oh, you're saying wait? Oh, I thought you were like, wait, like, hold on. Oh, I gotcha. Okay, what is the weight of a 2 kilogram object on the surface of Earth? Okay. So remember, mass and weight are not the same thing. So the force of gravity is actually the weight. It is a force, not a mass. Does anyone remember the formula for weight from the friction lab? How about Newton's second law? Anyone remember that? ma. So what is the mass of this block? 2 kilograms, right? What acceleration is this block experiencing? 9.8 meters per second squared, right? So guess what the formula for weight is? mg. You see where it comes from? It is Newton's second law. It's just because we're on Earth, we call the acceleration g. So they're one and the same, really. So to figure out the weight of this block, we're going to take 2 times 9.8. And if you do that, we get a F net, or a weight, I should really say instead of an F net, of 19.6 newtons. And I'm actually going to change that to weight. Because more than likely, if this object's sitting on anything, a table, whatever, it would be being balanced, and so it wouldn't be a net force, it would just be a weight. Okay. Last one. A 25 Newton westward force and a 35 Newton eastward force act concurrently on a 15 kilogram object on a frictionless surface. What is the magnitude of the object's acceleration? All right, this one to me begs for a free body diagram. So first thing I'm going to do is I'm going to draw it as a box. I'm going to identify the object's weight, the force of gravity, and I'm going to assume this frictionless surface is able to balance the force of gravity, so I'm going to call that the normal force, F sub n. I'm also just going to, just for fun, write down the mass of this object is 15 kilograms, just because it's something I know. I also know that there's a 35 Newton force headed to the east and a 25 Newton force headed to the west. Okay. I want to know what's the acceleration of this box. So just looking at this free body diagram, and hopefully you can see how this picture is useful, what is the net force on this guy? Very good, 10 newtons. Right? And it'll be positive because it's headed to the right. Can I calculate acceleration? Yeah. I think I can if I use Newton's second law, right? F net equals ma. So the net force is 10 newtons, the mass is 15 kilograms, and a is what we're looking for. And so if you do that little math problem, I get an acceleration of 0.67 meters per second squared. Oops, sorry, I got a little crazy. Notice how we're not just using any old force in F net. Had I put 35 newtons in there, you would get a totally different answer and, quite frankly, the wrong answer. It has to be the net force. Right? It can't just be any old force. All right. So hopefully that's useful for you.